Chapter 17, Quantum Vibration, Section 17.1, Classical Harmonic Oscillator. The potential energy of a harmonic oscillator is half kx squared. K is the force constant, and x is the displacement of the spring. So x is the actual length of the spring minus its natural length or equilibrium length. When x is 0, the potential energy V is set to 0. Hooke's law states that the force exerted to a spring is proportional to its displacement. F equals negative kx. We have a negative sign here because the direction of the force is the opposite to the direction of the displacement. And because F is equal to negative dV over dx, where V is the potential energy, and then we have dV over dx equals negative force equals kx. We can solve this differential equation. We get V equals 1/2 kx squared. Again, when x is 0, we choose to set the potential energy of the spring to 0. We now derive the vibrational frequency of this spring. So F equals ma, that's Newton's law. A is the second derivative of the length of the spring with respect to time. The equilibrium distance is independent of time. Therefore, force is equal to m times the second derivative of the displacement x with respect to t. And F is also negative kx. So now we have another differential equation. Again, this x is the displacement of the spring, or it's the relative position of the mass relative to the equilibrium position. X is not the absolute length of the spring. The absolute length or the actual length of the spring is the equilibrium length plus the displacement. The equilibrium length is also called the natural length of the spring or the free length of the spring when there's no force exerted on the spring. The differential equation of the motion of a harmonic oscillator is this. Really, it's just ma equals negative kx. Because force is equal to ma, force is equal to negative kx. We can reorganize this equation. We have the second derivative of x equals x multiplied by a constant, a negative constant. Well, this is really similar to the Schrödinger equation of a free particle. We can solve this equation. Two possible solutions are e to the power of plus I times the square root of k over mt. Another is e to the power of negative I square root k over m multiplied by t. Also similar to the solutions to a free particle. The general solution is a linear combination of these two solutions. So we have two coefficients here, c1 times e to the power of plus I square root of k over mt, and then c2 e to the power of negative I square root of k over mt. The square root of k over m is the angular frequency, omega. c1 and c2 are just constants. And because e to the power of I theta can be expressed as cosine theta plus I times sine theta, x can be expressed as a sine or cosine function of time, or the combination of these two. So x is a combination of a cosine function and a sine function of the square root of k over m multiplied by t. We can combine these two to form another sine function or cosine function. Here I'm showing a sine function. We just need to add an initial phase over here, alpha over here. So when time is 0, x is a times sine alpha. If we assume at time 0 there's no displacement and alpha is 0 in that case. Again, alpha is the phase shift of the sine function. The square root of k over m is the angular frequency of the sine function. B1, B2, they are arbitrary constant. Therefore, this A is an arbitrary constant. The angular frequency is equal to 2 pi times the ordinary frequency, denoted by nu. So omega is 2 pi times nu. The ordinary frequency of the harmonic oscillator is therefore omega over 2 pi, or 1 over 2 pi times the square root of k over m. By looking at this equation, if we have a larger force constant, a smaller mass, we have a higher frequency, and of course a higher angular frequency. Because the sine function is periodic with regular intervals of 2 pi, the period of the oscillation t of this sine function is defined by this following equation. So if we increment time t by uppercase T, well, the difference should be 2 pi if we're looking at the adjacent crests or troughs. Solving this equation, we get this uppercase T, the period of oscillation. It's 2 pi times the square root of m over k, and x can be written as a sine function of 2 pi multiplied by time divided by the period, and then plus some phase shift. The reciprocal of the period of oscillation is the ordinary frequency. So we get this equation again. This nu is the reciprocal of 2 pi times the square root of m over k. So nu, the ordinary frequency, is 1 over 2 pi times the square root of k over m, and the angular frequency is 2 pi times the ordinary frequency. For a two-body harmonic oscillator, we can separate the relative motion of the two masses, considered as the harmonic oscillation, from the concerted translational motion of these two masses. We can then solve the equation for pure vibration. So the idea is to separate the translational motion of the two masses from their vibrational motion. The derivation of the frequency of the two-body oscillator is the same as that for one-body harmonic oscillator, except all occurrence of m needs to be replaced by the reduced mass, and in the end we have the ordinary frequency nu to be 1 over 2 pi times the square root of k over mu. 1 over mu is 1 over m1 plus 1 over m2. Mu is smaller than m1, mu is smaller than m2. The two-body system may undergo translation as well, and if we define this uppercase as the total mass, this v as the translational speed of the center of mass, and then we have this equation: m1 v1 plus m2 v2 equals uppercase mv. And again, this v is the velocity of the mass center. The uppercase m is m1 plus m2. This uppercase v, the velocity of the mass center, is m1 v1 plus m2 v2 over m1 plus m2. This v is just, I think, the mass weighted velocity. Alright, so you need to take the mass into account. The top, you have the momentum of mass 1, you have the momentum of mass 2. So in total, you have the momentum of the entire system. On the bottom, you have the mass of the entire system. And this uppercase v is the velocity of the entire system. We can prove the sum of the translational energy of the two-body system and the vibration energy of the two-body system is equal to the sum of the kinetic energies of the two separate bodies. So really we want to prove this 1/2 mv squared. This is the translational energy of the two-body system. 1/2 mu times v2 minus v1 squared. This is the vibration energy of the two-body system. We want to prove the sum of this is equal to 1/2 m1 v1 squared plus 1/2 times m2 v2 squared. So this is kinetic energy of mass 1, kinetic energy of mass 2. When we sum them up, we get the total kinetic energy. Over here we have kinetic energy of the translation, kinetic energy of the vibration. We sum it up, we get the total energy. The derivation is simply just some algebraic operations. First, we replace the uppercase M with M1 plus M2. V is M1 V1 plus M2 V2 over M1 plus M2. So we have this expression, and we have the vibration energy. So what we're going to do is we try to simplify the expressions. For example, we have m1 plus m2 squared on the bottom, so we clean up a little bit. We get this expression on the left. Mu is m1 m2 over m1 plus m2. We have that on the right. And we see 1/2 is a common factor. 1 over m1 plus m2 is a common factor. And then we sum up everything. The first three terms come from this, and the last three terms come from m1 times m2 times v2 minus v1 squared. So you see m1 m2 here, m1 m2 here, and m1 m2 here. And then we clean up a little bit. We look for things that we can cancel. This term 2 m1 v1 m2 v2, negative 2 m1 v1 m2 v2, they cancel. So we have only 4 terms left, and we can further separate these 4 terms. We find v1 squared, we'll put them here. We find v2 squared, we put them here. Now this divided by m1 plus m2, we get m1 v1 squared over here. And this divided by m1 plus m2, we get m2 v2 squared. So we proved that, well, the total kinetic energy of this two-body system can be done in 2 different ways. One is we can have the kinetic energy of m1, the kinetic energy of m2. We sum up these 2 values, we get the total kinetic energy. Another way is to look at the translational motion of the entire system and the vibrational motion of the entire system, and then we sum up the translational energy and the vibration energy. We also get the total kinetic energy.